This recording documents the early development of a small homemade steam locomotive model. You will learn how the machine was constructed, the principles behind its operation, and the problems encountered during testing. Although it was designed to run on live steam, the current version operates on compressed air, supplied by a workshop spray gun compressor. Physical description. The locomotive measures 18 centimeters in length, 10 centimeters in height, and 7.5 centimeters in width. Its spoiler is made from a repurposed aluminum energy drink can. A steel nut is fixed to the top of the boiler. A removable bolt serves as a fill cap, allowing water to be poured inside. Steam or compressed air from the boiler is carried through metal tubing to the drive units, mounted on both sides of the chassis. The locomotive uses two oscillating steam engines, identical in design to the one shown in the previous workshop log. Each engine cylinder is a 15mm segment of aluminum tubing with a 10mm bore and 1mm wall thickness, mounted on a pivot so the entire cylinder can swing as the piston moves. Unlike the single-cylinder demonstration engine, these twin engines do not require a flywheel. Instead, they work in opposition. When one cylinder aligns with the intake port, the other lines up with the exhaust port. This alternating cycle keeps the wheels turning continuously without the need for stored momentum. The entire assembly is fixed to a simple metal frame with a boiler at the top and the twin engines driving the wheels directly. Intended operation. The original plan was to heat the water in the aluminum can boiler using solid fuel tubes placed beneath it. Boiling water would create steam that would pass directly into the twin cylinders, powering the locomotive without external equipment. In theory, the alternating action of the two oscillating cylinders would provide smooth rotation of the drive wheels. Test results. In practice, the boiler and sealing proved inadequate for live steam. Heat from the open flame softened the hot glue joints that had been used to hold some small components such as bearings to the frame. More importantly, the boiler never built up enough pressure to move the pistons effectively, likely due to a combination of low heat transfer and leakage around the piston seals. For demonstration purposes, the model was connected to a spray gun workshop compressor. On compressed air, the locomotive performed far better than expected. The cylinders cycled smoothly, the wheels rotated continuously, and the twin-engine system proved that the mechanical design itself was sound. Next steps. Future upgrades will focus on improving the boiler and seals, and possibly adding a manual valve between the boiler and cylinders. This would allow pressure to build up before being released all at once, which could produce at least a few seconds of motion under its own steam. Hot glue joints will be replaced with more heat-resistant mounts to withstand real flame. Despite the challenges with live steam, the compressed air tests demonstrate that the drivetron works as intended. The locomotive stands as an encouraging step toward a fully self-powered steam model, showing how even improvised materials can achieve functional motion. Further refinements to the boiler and fittings will continue, but for now, the early results are promising.